Hello, this is Mitchner. Here we go again. We are doing section 4-5 notes and starting up with the beginning here of just reviewing a little bit of the second fundamental theorem of calculus. First example, just to kind of review a little bit, I have f of x equal to, well, you can read the problem there. I want to integrate it first of all and then find the derivative of that. So basically I'm doing the derivative of the integral from 0 to x of t times t squared plus 1 dt. Now, this is maybe going through without the shortcut, just kind of showing you once again how this works and making sure that you understand it. What I'm going to do first of all is I'm going to do the integration. And before I do that, I'm actually going to distribute that t. So I would get a t to the, did I write that problem right? Yep, t third plus t to the first power dt. And then I'm going to actually do my integral. So that would be t to the fourth over 4 plus t squared over 2, and evaluating that from 0 to x. So doing inside the brackets, I'm going to get x to the fourth over 4 plus t, make that x squared, over 2. That's the first one, plug it in x, minus, now just plug it in 0. So what I get then is now the derivative out front of 1/4 x to the fourth plus 1/2 x squared. Now if I perform the derivative on that, I am going to take 1/4 times 4 x to the third power plus 1/2 times 2 x. And I see that those cancel, so I'm back at x to the third plus x, which, as you can see, that's what I had before, just substituting in our x instead of having t. So f prime of x would be equal to x cubed plus x. Okay, so that's example 1. If I go on then with example 2, I'm just going to use the shortcut for that. Example 2, I have the derivative of the integral from 0 to x, the square root of t squared plus 1 dt. Since the top value of that integral is just an x and the bottom number is a 0, I can use the fundamental theorem of calculus, which just states I have the square root of x squared plus 1, and I'm done on that one. Now, on the next one, it's not quite so short and sweet, I guess you could say. I'm going to show you on example 3, not using the shortcut, showing you why we have to do the derivative of the x cubed. So there's the problem. I'm going to first of all do the integral. Do this portion of it. And when I do the integral of cosine, I am going to get the sine of t, and evaluating that from, at the top I have an x cubed, down here I have an x, or pi over 2. So when I substitute in, I'm going to get the sine of x cubed minus the sine of pi over 2. That's what I get when I have the integral. Now I'm going to do the derivative of that. Taking the derivative of sine, I would get the cosine of x cubed. Now that's just like the chain rule. I have to multiply by the derivative of x cubed, which is 3x squared, minus sine of pi over 2 is just a constant, so that's just going to be 0. So as you can see right there, not only do I just substitute in my x cubed in for the t, but I have to multiply by the derivative of that x cubed, which is 3x squared. And there is my final answer on that. Okay? Alright, so the next one I have here is the anti-differentiation of a composite function. And you can read that box, and there's all the formal definition of that. And basically what we're going to do is we're going to take a problem and try and make it a little bit more simpler. Make it look easier to work with. So here's the problem. I have the integral of x squared plus 1, the whole thing squared, times 2x dx. What I'm going to try and look for is what would be a good value to substitute in just the simple u. Now since this parenthesis is raised to the second power, I'm going to let that be my u. So I go over here and I say, okay, let's let u be x squared plus 1. Now if you look back in the formal definition, I have to have a du as well. So my derivative of u with respect to x is going to be a 2x dx. So what I can do is I can substitute in right here. There is up in my equation my 2x dx. That is my du. So I can rewrite this whole integral in terms of a different variable u du. Now that looks a little bit simpler to work. If I do the antiderivative of u, that is u squared. Whoops, I wrote it down wrong. You caught that mistake, didn't you? That would be the integral of u squared du because of that 2, boom, right there. So if I want to do the antiderivative of u squared, I would get u cubed over 3 plus c. And I look at that and I'm done. So I'm going to rewrite that. Instead of u, I'm going to plug in the value we picked out, which was x squared plus 1. So there it is. That problem done with substitution. Because I have composite functions, I can do that. Okay? Example 5. Example 5 is the integral of the cube root. So I'm going to rewrite that as 1 minus 2x squared to the 1/3 power, and then I have a negative 4x dx. Okay, again, when you're using substitution, sometimes it's a trial and error, and one of the things I look for is something raised to a power. So I have 1 minus 2x squared raised to a 1/3 power, so I'm going to let u be my 1 minus 2x squared. So my derivative of u is going to be negative 4x dx. So I look up here, do I have a du up here? Yes, I do. I'm lucky on this one. Will not always work out that way. So then I rewrite this integral with my value of u substituted in. That is u to the 1/3 du. And then I can do the antiderivative of that. So I'm going to get u to the 4/3 times 3/4 plus c. And my final answer is 3/4. Substitute in your u value, gosh, I forget what it was already, 1 minus 2x squared to the 4/3 power plus c, and there is our answer. Okay, now I know I'm talking a little fast, so feel free to ask somebody to pause it so you can get caught up on filling in your notes. That's 5. So example 6. Okay, example 6. We all need to be ready for example 6. Everybody paying attention? I have t cubed. I'm going to rewrite this as t to the 4th plus 5 to the 1/2 power dt. That radical I'm just going to go ahead and change to a 1/2 power. Okay, once again, inside the radical, I'm going to let that be my u, which is t to the 4th plus 5. And then my derivative of that is going to be 4t cubed dt. Now, I have a problem here. I have the t cubed dt, and it's okay that it's separated because we know multiplication is commutative and I can move it down there. But I'm missing that 4. Uh-oh. What are we going to do with that? Well, this is something that you can do here. Can I multiply by 1? And the answer is, of course I can. So I'm going to multiply by a 4 over there and a 1/4 over here. So basically I've multiplied by 1, and now is the 4 there. So now I can rewrite this as, now that 1/4 out front needs to be there. Here's my u to the 1/2 power times du. So you can insert a constant there as long as you multiply by its reciprocal as well. So now I'm ready to do the antiderivative of u to the 1/2. So that's 1/4. That would be u to the 3/2 times the reciprocal, which would be 2/3 plus c. So I get basically 1/6 u to the 3/2 plus c. And then I go through and I substitute back in my value for u, which is t to the 4th plus 5 to the 3/2 plus c. And that's my final answer. Okay. Example 7. Let's do another one where we have to insert some things. I have the integral of x cubed, and I'm going to go ahead and rewrite that. 1 plus x to the fourth to the negative second dx. Again, I'm going to let this part be my u. So I'm going to let u be equal to 1 plus x to the fourth. Therefore, du in differential form, I can't say the word today, differential form, oh my goodness, is 4x cubed dx. This is actually the third time I'm doing this lesson because the first two recorded lessons crashed. So this is the third time today I'm doing this. Guess I'm getting tired of talking to nobody out there in the classroom. So glad you're here to listen to me today. So here we go. Next one is, next step, I'm looking for my du. I've got my x cubed dx. I do not have the 4, so I'm going to insert a 4 as well as a 1/4. So I'm multiplying by 1/4 times 4, which is just multiplying by 1. Perfectly legal. So I rewrite this with the 1/4 integral of u to the negative half du. I can do my antiderivative. That would be u to the negative 1 over negative 1 plus c. So I get negative 1 over 4u plus c, which is going to be negative 1 over 4 times the quantity 1 plus x to the fourth plus c. And there is my answer. Example 8. I have the integral of x times, oh, let's rewrite this. Let's rewrite this as the sine of x squared, and I'm going to move the x dx down there together. Again, on this one, I'm just going to kind of randomly pick this u right here to be x squared, so the derivative of that would be 2x dx, or my du would be equal to 2x dx. If I look here, I have an x dx, I'm missing the 2. Multiply by 2, pull out a 1/2. I guess I didn't really mean pull out a 1/2, I mean just kind of write a 1/2 out front. So this is my u right here. All this is my du. So I rewrite this as 1/2 times the integral of sine of u du. So I can do the antiderivative of sine, and we all know that that is negative cosine of u plus c. Substituting back in, I would get the cosine of x squared plus c. That is my answer. Okay? Again, pause if you need to. Next one is example 9. I have the integral of the square root of tangent of x times secant squared x dx. Okay, again, another hint I'm looking for is I see a radical, so I'm going to look inside that radical and let my u be tangent of x. I'm also thinking ahead because I know that the derivative of tangent is secant squared, so d is going to be secant squared x dx. Again, I need that in differential form. And I'm really happy to see right there that that is my du. So there's my u, there's my du. So I can rewrite this as u to the 1/2 power du. I like this problem. So rewriting this, doing the antiderivative of u to the 1/2, I would get u to the 3/2 times 2/3 plus c. And then I do my substitution. I would get 2/3 times the quantity tangent of x in parentheses raised to the 3/2 power plus c. And now keep in mind, sometimes you will see this written as tangent of 3/2 right there, x plus c. Either one is acceptable. I have to say, every time I've taught this lesson today, it's gotten shorter. So I guess I'm really either talking fast or not adding any commentary. Here we go. I'm getting bored. I have nobody in the classroom. I'm just sitting here talking to myself. I'm feeling kind of lonely and bored. I gotta quit rambling and get the problem done. Here we go. Example 10. This is a prime candidate for you have choices. You can pick u to be sine of x. You can pick u to be cosine of x. It doesn't really matter. Now, one thing you need to keep in mind is some of these problems, depending on what you pick for u, our answers will look different, but they will be equivalent. And what will happen is they will actually just differ by a value of a constant. So anyway, don't worry about them looking different if you pick a different value for u. There are some problems out there where you'll have different answers. Okay, so on this one I'm just going to randomly pick sine to be my u. I'm going to let u be sine of 4x. Then I don't have to worry about a negative. And then I have the derivative of that to be the cosine of 4x times 4 dx. Don't forget that 4. The chain rule, we have to use the chain rule on this one. And I'm looking up here, I have my 4x dx, but I am missing the number 4. So I'm going to squeeze in a 4 there, multiply by the reciprocal out front. So I get a 1/4 integral of u du. Oh, that's a really easy problem. So I get 1/4 u squared over 2 plus c, which is 1/8 u squared plus c. Now, don't forget, a lot of people will forget to substitute back in. That makes it really wrong. So I need to put that sine of 4x back in. Since the whole quantity is squared, this is one of those that it can be written either way. You can write sine squared right there as well. Okay, example 11. Example 11 is just one that just throwing in here that you do not have to always use substitution. Substitution is now just a new tool that you can use. This is a problem we've had probably something very similar to this. I'm going to bring that radical t up as t to the negative 1/2. And then distribute. So I get a t to the 1/2 plus 2t to the 3/2 dt. Now I'm ready to do my anti-differentiation. 2/3 t to the 3/2 plus 2 times 2/5 t to the 5/2 plus c. So one acceptable answer is right here. Another one would be to factor out your greatest common factor. My greatest common factor would be, how about, okay, we got to think about this. Common denominator here would be 15. This is the same as 4 out of 15. No, it's not. This is the same as 15 times 5, 10 out of 15. And this is 12 out of 15. So if I look at that, bringing out my greatest common factor as a fraction, wouldn't that be a 2 out of 15? And my lowest exponent of t would be t to the 3/2. So what do I have left? I would have 5 here. I would have 6t here plus c. Bingo. There it is. So I don't really care which one you use, but sometimes that second one will be very helpful in evaluating some things. So I just wanted to kind of bring that up. Okay, so third time's a charm. It's got to work this time because I'd rather have me teaching you this and you trying to look at the notes and trying to figure them out. So what you need to do is maybe work together on your homework, ask each other questions, and make sure you get that done today. And make sure you are ready for a nice little homework quiz. Just something real short so I know if you know what you're doing or not on the homework that was due today as well as this homework. Now, make sure that you take the time to check homework, ask each other questions. I expect all those questions to be answered today in class. You've got classmates that can help you out. Okay? Thanks a lot. You guys have a great day, and I will see you next class period.